Part 7, Power. Let's recap a bit. What is the cumulative effect of a net force acting on an object over time? Well, the impulse momentum theorem says that the impulse imparted to an object by a force acting over time represents a transfer of momentum. A force acting over time transfers momentum. And our impulse momentum theorem is EJOP for short. What does a net force do over a distance? The cumulative effect of a force acting on an object over a distance. We call that the net work done on the object by the force, and we've seen that that represents a transfer of energy. Transfers energy, a force acting over a distance, pushing an object along a path. And that is EWOK, EWOK for short there, our work energy theorem. Now, let's examine the instantaneous rate at which a force transfers momentum and energy. So a force acting over an infinitesimal time interval, dt, transfers an infinitesimal bit of momentum, dj. So a tiny impulse, dj, is imparted to an object by a force acting on it over a tiny amount of time. So you advance time forward a little bit, and that force will impart a tiny impulse to the object. There's no particular name given to the instantaneous rate at which a force transfers momentum. The rate of the transfer of momentum. So the rate at which the impulse is imparted, dj dt, but we see by taking this and just dividing both sides by dt, we get this expression. A single force acting on an object imparts an impulse at a rate that's equal to the force itself. Now, if we make this the net force acting on the object, so this was the rate of imparting a net impulse, then we could rewrite that as the familiar Newton's second law. The rate of change of the object's momentum is due to the net impulse imparted to the object. That is the impulse imparted by the net force. So the net version of this statement is Newton's second law. Okay, so that's the rate of transferring momentum. But a force acting over an infinitesimal displacement, dr, transfers an infinitesimal bit of energy, a tiny amount of work that's done, dw. So when a force pushes on an object over a tiny step forward, the object takes a tiny step along its path, then a tiny amount of work is done by that force. Positive, negative, or zero work is done by that force, this tiny amount dw. So the instantaneous rate at which that force is transferring energy, that rate does have a special name. I pointed out up here that there's no special name for the rate of transferring momentum, but the rate of transferring energy does have a special name. We call that power. The power input or power output from that force that's doing the energy transferring. Power is defined as the rate of transferring energy, so we take this expression here and divide both sides by dt. So power is the rate of doing work, dw dt. So F dot dr over dt. And dr dt, that's exactly the definition of velocity. So take the force acting on the object and dot it with the instantaneous velocity of the object. That dot product gives you the instantaneous rate at which that force is transferring energy to or from the object. So the instantaneous power input or output to or from the object. So there we go. There's our definition of power, and we see these two equivalent ways of expressing it. Both are useful. dw dt, so the work done over time, the instantaneous rate at which energy is being transferred, or in terms of force and velocity, the dot product of those two vectors. One other way we could rearrange this expression here would be to multiply both sides of this by dt, and note that a tiny amount of work is done given some power input and a small amount of time. So given some power input, advance time a little bit forward, and that product represents the tiny amount of work that was done during that time. So adding up the effect of power input output over time can give us the total work that's done over some interval. So the total work done over some interval comes from adding up all the little bits of work that are being done. Interval means adding up an infinite number of infinitely small things, so add up all those little bits of work. Each dw is given by p dt, so if we integrate the power acting over time, so this power itself could be a function of time, integrate that over time, or replace that power with f dot v, force dotted with velocity. That could be our integrand as well. So these integrals here are our way of finding the total work that's done over some time interval. Since we have a derivative definition here for power, we could convert that into an average power expression. So the average power input or output by a force. Average power, P average, can be found just by replacing the derivatives here with deltas. So delta W over delta T. The thing is, a work always represents some change or some transfer in energy, so we never write delta W. The work is already understood to be a small a change in energy. So replace this with the total amount of work done, W, and replace dt with the total time that's lapsed, delta t, and that gives you the average power input or output during that time interval. Okay, so with those definitions, one more note here about units. The SI unit for power is the watt, named after the Scottish engineer and scientist James Watt. 1 watt is defined as 1 joule per second. So they're equivalent. A watt is a joule per second. And we run into an issue here, a notational issue. We are representing the quantity work by a capital W. Capital W stands for work done, but the unit for power is the watt, also written as a capital W. So there's a potential for confusion here between capital W for work and capital W for watt, the unit of power. So if you're handwriting things, I recommend trying to find some way to distinguish your W for work from your W for watt. I personally like to put a couple of serifs there on the W for watt. Sans serif for work, little serifs on there for watt, just to help make that distinction. A unit you might be familiar with is the English unit for power, horsepower. 1 horsepower is equivalent to about 746 watts. There's the conversion. And it comes from this idea here. Suppose you've got a 75 kilogram load here being lifted by a horse, which would have been employed in the mining industry in England at the time when these technologies, steam engine technologies that James Watt worked on, were being developed. So your horse was hauling your loads in and out of your mine shaft. So if you've got a 75 kilogram load here and you need to lift it up a height of 1 meter, you have to apply a force to do that. You have to apply a force to that load over a distance. You have to do work on that load to lift it up. And of course, time is money, so you care how long it takes to lift up that load. So 1 horsepower is defined as the the power output of a horse or a machine or a thing that can lift a 75 kilogram load 1 meter in 1 second. So the rate of doing this much work in 1 second, that's equivalent. That's the origin of the definition of a horsepower here. And you can see in this list some example power outputs by automobile engines, if you want to get a sense for how much a horsepower is. And then here also is this statement I got from Wikipedia about human power output possibilities. So you can read that yourself.